let's just make sure you're on the right track here. Start out with the volume. Of course, to find the volume, find any of these, the volume or the surface area, you have to have the area of the base. And of course, the base is this messed up thing out here. We can divide it into 4 or 6 different sections, depending on how you want to do it. We need to know this dimension here. Can anybody tell me what that dimension is? 4. Because we've got 8 here. 8 is 16. Plus this 6 would be 22. This 4 would make it 26. Out of 30, there's got to be 4 more. Everybody see where that 4 comes from? Okay. So now, should I cut this here too for the half circle? Section 1 here is a half circle. So that'll be pi times 8 squared divided by 2, which is what, about 100.48? I'll move that over a little bit. Square inches. Section 2 here is just 8 by 16, or 128 square inches. Section 3 is a trapezoid. So it's 16 plus 8 over 2 times 4. Everybody see where those came from? Now trapezoid, it's the average of the bases. This is 16. This is 8. So you're adding them together and dividing by 2 to get the average of them. Because we're getting a, remember this is a rectangle. It's the halfway between those two. And then times the height of 4. So that is, what, 20 times 4, or 80 square inches. Then this one is 6 by 8 for section 4. 48 square inches. And then, of course, the last one is a half circle. Section 5 is a half circle, radius 4. So pi times 4 squared over 2, which is what, 25.12 square inches. So what do we get there? 1, 2. I get 381.6 square inches for the area of the base. Does that sound right? Anybody else get that?
Number 3, I think, is calculated wrong. I'm about to do it.
6? Oh, yeah. Yeah, that should be 12, not, that should be 48, not 80, right? Does that look better? So what's that give us then? 49, 349, so 381. Does that sound better? How many did 349.6? Okay, well, if you didn't have that, now you know, you need to know where you need to go back to. I'll have those sections there. You may have divided it up slightly differently, but I'll put them there so you can see it. 349.6 is what we had for the area of the base. I'll write that in there too so you can see that part. I'll pause this so you guys can work for a little bit. So then, of course, our volume from there is simple. 349.6 square inches times the 30 inches, which is going to be what? What's that? 10,480? 88 square inches. That works. So there's our volume. We're going to come back to that in a minute. That'll be cubed. You are correct. It's just cubed. Thank you. So there's our volume. Next, we need to find surface area. To find surface area, we need the perimeter of the base. Or actually just find the lateral area, so we need to find the perimeter of the base. Well, I have 8 and 8, 6 and 6. So let's do those first. Then I have this slope piece here, which is actually 4 by 4, right? Which would make the length of it the square root of 4 squared plus 4 squared, right? Sound look familiar? So 5.66 plus 5.66 plus, then we got the half circles. Half circle with radius of 8, so pi times 16 divided by 2 is 25.12. Then pi times 8, the half circle radius of 4 divided by 2, 12.06, right? Or 12.56, I should say. Which all adds up to a mess. What do we got there? 28, 38, 39.32, 39.44, 40, 60, 77. Is that what that adds up to? 77 inches? Ish, somewhere in there, yeah. So then our lateral area is that perimeter of 77 inches times the 30 inches. Do we divide by 2? Say no. There you go. So 2,310. Why would we ever divide by 2? If it was a pyramid or a cone, we would divide by 2 because they're triangles because it goes up to a point, right? That's volume would be divided by 3 on a pyramid or a cone. So we've got our surface area. 2,310 is the lateral area plus the area of our base. 349.6 and 349.6. $3,009.2 sound about right for our total surface area. 3,010 somewhere in there. Somewhere over 3,000. Good enough. So now 1.3 grams per cubic centimeter density and 10,488 cubic inches. But in order to use this density, we have to change it into cubic centimeters. 1 inch cubed is how many centimeters cubed? We did say that 1 inch is 2.54 centimeters. But to cube that, we got to do 2.54 to the power of 3. 16.39 centimeters cubed per inch cubed times 10,488. $171,867.5. Cubic centimeters. Now I'm going to multiply that times the 1.3 grams per cubic centimeter. Gives us 223,427.8 grams, or most likely change to 223.43 kilograms. Or if you want to change it into pounds, roughly 491.5 pounds. But we'll stick with the grams and kilograms. Either one of these would have been fine. Did anybody actually get that one? One person? Gotcha. So that would be a really good extra credit question on a test someday. You won't be answering that extra credit?
If I happen to get her right.
Yeah. Well, what we're going to look at today, we're going to look at some, and I'm sure you guys have seen this more than once, What's that mean? Plus or minus 3 thousandths. Yeah, we've seen this before, right? That means we can be a little bit bigger, a little bit larger by 3 thousandths. Of course, that implies a range. What's the range that this implies? 0.277 up to 0.283 inches. Look familiar? What's that? Okay, so for this one, what's that implying? It can be a little bit bigger, but not any smaller. So what range does that imply? Yeah, 1.2, that's 1.2. Yeah. Up to 1.210. Yeah. So, this is what we call, of course, unilateral tolerance. Because it only goes in a single direction. This is called bilateral because it goes in 2 directions. But if I give you a range, you should be able to go back to a bilateral tolerance. So if I wanted to convert this into a bilateral tolerance, we have this desired value. How do I find that desired value? I'm just going to average together the upper and lower limits, right? 1.200 plus 1.210 divided by 2, 1.205. Then the tolerance itself, or the allowable error, which is this number here, the plus or minus, I got to be careful because that's technically not a tolerance. The tolerance is actually the difference between the minimum and maximum. This is a 10 thousandths tolerance. Like here, this is a 6 thousandths tolerance. It's plus or minus 3. There's a tolerance of 6 thousandths. So you got to be very careful. This is an allowable error, not a tolerance. So that allowable error, I just take this number here, the 1.205, subtract either one of those. Usually it's easier to subtract the small one, get 0.005. So if I wrote 1.205 inches plus or minus 0.005 inches, I get the exact same range as I do for this. So why would I write it this way? Yeah, in an ideal world, I want it as close to 1.2 as possible. But I can be over by as much as 10 thousandths, just cannot be under, period. So remember, this is not talking about the capability of your machine. Let's say you have a machine that will always go plus or minus 2 thousandths. That you are relatively confident that 99.9% of the time, that machine can get you within 2 thousandths. So what are you going to set it at? Well, you're probably going to set it at 1.202 or 1.203 or somewhere in there, so that you know that even if you're 2 thousandths below, you're still above the at or above the 1.2, or 2 thousandths above, you're still within your 10. So this is not saying anything about the machine. This is saying about the functionality of the part. You know your machine, so you know where to set it at. If I'm giving you this, though, you're just going to target the 1.205 and go there, and all your parts are going to get, I mean, yeah, they're all going to be, most likely all going to be within tolerance, but they're going to be further away from your desired value than you'd really like them to be. If we were to get into like a statistical process control, which in the spring, if we really get some extra time, which we haven't since your program started, when we had the 2-year program, sometimes we got some extra time, but what you'll find is you guys have all heard of the bell curve, right? Any machine, when you manufacture parts, manufactures into a bell curve. Of course, the average or the mean size of that part is going to be right in the middle of the bell curve. But let's say that you wanted this to be 1.200 inches. You set the machine at 1.200. Well, there's a standard deviation, they call it. If you actually measured every part coming off that machine, you can do some calculations. And you would find that, okay, you go out so far, and like 68% of all the parts are going to fall within that range. And 95% of the parts are going to fall within the next range out, and so on. You go out, it's called 3 standard deviations. You guys ever hear of something called 6 sigma? It's a quality control thing. A standard deviation is called 1 sigma. So you're going 3 sigma or 3 standard deviations on each side. That's where you get the 6 sigma. 99.7%. If your machine is set up correctly, 99.7% of all parts should be manufactured within 6 sigma or within 3 sigma of the mean, but within that 6 sigma range. If you have more than 0.3% or 3 out of every 1,000 parts falling outside that range, there's something wrong with your process. Half will be undersized, half will be oversized, yes. Yeah, well, this is your mean, and if you're setting it at your mean, whatever you set the machine at should be your mean. Yeah, and half your parts will be smaller, half of them will be larger. They talk about something called tinkering. It's an Edward Deming. It's actually a William Edward Deming, but he always went by Edward. Talked about tinkering, where you run like 3 or 4 parts, and they're all a little bit too small, so you adjust the machine. He talked about how many parts you really have to run to get a true measurement. And it's way more than you would think. A lot of people will run a batch of 4, 5, 6 parts, and they'll measure them, and well, they're all a little bit too small. Well, the chances of getting 4 parts in a row that are too small are way better than you would think. It's like 6.25% chance, which sounds small, but still in manufacturing you want to reduce that. In manufacturing you want to be under 3% chance of before you make any adjustments. Does that make any sense? So in manufacturing, I think it's a minimum of 6 parts in a row that you have to have that are undersized before you start to worry about adjusting the machine. Because it's something called tinkering. He described it as a bullseye. If you have your parts being produced, they fall like that naturally. But if you start after every part, if you say, okay, my first part was this one here, it's a little too small, so I'm going to adjust the machine. Well, your next part's going to go over here instead of right there, because you're going to overshoot the adjustments. But that's kind of outside the math course here. I got off on a tangent. Have we talked about clearance and interference fits in here? We mentioned them briefly, didn't we? Okay. Let's look at for an engine block, a frost plug. What holds a frost plug in? Friction. The fact that the plug is slightly larger than the hole. So let's say that this is a 0.750 inch plug, plus or minus 0.004 inches. My hole is 0.740 inches, plus or minus 0.004 inches. This is what we would call an interference fit. What is the smallest the plug could be? What's the largest the plug can be? Smallest the hole can be? 736.744. So our interference our minimum interference comes when the plug is small and the hole is large. What's that come out to be? 0.002. Our maximum interference comes when the plug is large and the hole is small. That is what, 18 thousandths? So you can see there's quite a range there between, the minimum and maximum. That minimum 2 thousandths, it's not going to take a whole lot to pop that sucker out. 18 thousandths, it's going to take quite a bit to press that thing in. So when we're dealing with two parts that have to interact with each other, we have to talk about this. Is called an interference fit. A clearance fit, because the two parts have to interfere with each other or they're not going to stay together. It's a pressure fit. A clearance fit might be a locator pin. Like if you put an alternator on some larger equipment or a starter, there's a locator pin. So you slide it over that pin and it holds it in place to get the bolt started. That needs to slide in and out freely. Or on like your brake calipers, they've got a pin that they need to slide back and forth on. That has to have clearance where that pin has to be smaller than the hole so it can slide freely.
It's gotta be greased.
Well, it helps if it is. Yeah. It needs to be free, put it that way. Whatever method you use to keep it free. I'm going to give you a packet. Actually, you know what? No, I'm not going to give you a packet quite yet. In your little book, talk about Unit 23. Actually, you know what? No, it isn't a packet. Unit 23 and Unit 29. I'll hand the packet out to you right now.